BA in Grenoble in collaboration with Lucky. Currently, he works at the London Center for Nanotechnology at UCL. Let's welcome Dr. Villis.
Excellent. Okay, well, I guess now we've got a bit of a change from all the theory and aim for something slightly more experimental now. I've been looking at the optical response of field effect transistors. And today I'm going to talk about what we've been able to discover from these relatively old-fashioned field effect transistors, quite large scale. People might remember these from their stories their grandfathers used to tell them about transistors. Looks like I need to be on the internet. Okay, yeah, so I've used Fourier transform infrared spectroscopy to do a lot of the optical measurements, but also I've done a little bit of measurements here that have incorporated the use of the free electron laser at Nijmegen in the Netherlands, and that's the Felix facility. So a lot of this work was done with people from London Center for Nanotechnology at UCL, but also we have a collaboration with Yu Xiaomei at Peking University, and also a few people at Surrey University, just to name a few. There's other people, of course, involved in this research. So really, computers have come a long way over the last few centuries since the advent of the abacus in the 14th century, and really have come a long way to the sophisticated integrated circuits that we have today in our computer chip. And also, I think, as people have identified, we've got a very long way to come before we reach the single atom future computers that no doubt will dominate a lot of the computational power in the future, or for particular types of computation. So really, a computer is basically, in the fundamental sense, a computer is made up of transistors. A transistor is just a three-terminal device that you can shut on and off a current by the application, by a bias on a gate contact. Very simple stuff, nothing new there. So really, it's not very clear, is it? One of the important things with giving a talk like this is really trying to identify a modern form of Moore's law that's up to date. Here, it's only actually current to 2008. Things have actually changed quite a bit. So I've had to actually add my own dots. But as you see here, we're up to about 6.8 billion transistors in a single integrated circuit. This is actually an FPGA card, so it's no longer a PC. But what's interesting, I find personally, is that we're deviating from this line a bit. We're starting to become more concerned with computation devices that no longer fit on this curve. And so obviously the iPhone, tablet PCs and that type of thing deviate from this curve. So I'm not sure if this means that we're ending Moore's law, but we're also becoming concerned about computation that exists outside of Moore's law. Obviously, another hope for this kind of computation is to be able to incorporate quantum mechanics into the bank of computational power that we have before us. Obviously, this involves the use of entanglement and superposition of both the on and off states of a regular transistor. I won't go into that too much. So really, a lot of what's driven my research is Bruce Kane's proposal of the silicon quantum computer. This is probably nothing new to a lot of people here. But basically, what this device consists of is a sequence of qubits that are defined by individual donor atoms in a silicon substrate. What's important here is we have two different types of gates. I'm not sure if it's clear. But you have an A gate here, a J gate, an A gate, which defines the electrostatics of each donor, which allows for the orientating spin of individual donors. But then you also have a J gate, which provides a mechanism of entangling your donor atoms. Bruce Kane's idea was to use electrostatic gates for coupling donors. But really, when you start to look at the mechanics of this mechanism, it's not that efficient. So the late Marshall Stoneham came up with an idea of using an intermediating donor atom between your two qubit atoms. Gabriel talked about this a little bit yesterday, so I won't spend a lot of time. But the idea is, for example, in this scenario, you might have two bismuth donors with an intermediating phosphorus donor here. So what's important about these donors is they have a degenerate excited states. So even though the ground state energies are quite different, the excited states are degenerate. So if we then position these donors if we position these donors far enough apart, so in the ground state they're non-interacting, then, but if they're also close enough that the excited states overlap, by selectively exciting the intermediating donor, or the phosphorus donor, you can get its wave function to extend over the two other bismuth donors here. So in this way, you effectively can couple or turn on coherently the exchange interaction between two qubits. So in this way, you're really making a more efficient J gate that can be controlled coherently. Okay, so worthwhile just spending a little moment on talking about the excited state spectrum, because that's quite important to a lot of my research. Basically, as Gabriel also quite clearly described yesterday, you can understand these by just taking the simple hydrogen model for the excited states and scaling these for the permittivity and so the effective mass of an electron in the silicon substrate. So here is just a few models, a few images of the wave function extent of some of these excited states in silicon. So here's a 20 nanometer size scale down here. What you see is you move to something like the 4p state, and you're already existing over quite a large region of your substrate. So no longer dealing in single atoms, this can exist over quite a large region. So in a way to measure these excited states in an ensemble or in a bulk sample, they're actually quite easy to do. There's quite a few studies over many decades that have looked at these excited state spectrum. And here's a good example where they looked at the temperature dependence of excited state. And you see at elevated temperatures, you start to see transitions from high 1s states to further excited states. And another important note about this kind of measurement is that if there's any kind of strain inside the silicon device, that perturbs these excited states and changes their energy here. But another important note here, the actual energy level that we're talking about is much greater than that used in sort of Zeeman splitting when you're talking about the individual energy of spin states in an atom. So really these are quite large energies in the sample. So one example that's looked at this kind of absorption spectroscopy is, Gabriel also explained earlier yesterday, that was this coherent control of the Rydberg states where they would form a Hahn echo measurement and see the beginnings of a Rabi oscillation in this kind of measurement. So this technique is quite useful for seeing quantum effects in silicon, but it would be really quite nice to move towards a smaller number of donors and be able to measure these effects without using a huge ensemble of atoms. These, I think, was like 10 to the 12 donor atoms, or something quite large like that. So with that in mind, the only real way to do that is by actually performing the detection inside the device. So with that in mind, we've moved to these field effect transistors that are, as I said earlier, quite large, quite old-fashioned in a way. They're hundreds of microns in size. But nevertheless, they work quite well, and we can do a lot of quite interesting experiments by using it. So if we just look at the cross-section of these devices, they're made with silicon insulator, so with a silicon layer of 1.6 microns. On top of this was a buried oxide. But we wired up these devices such that you could bias the handle layer and then form a backgate. So really it's just a backgated transistor device, quite large in size. These devices are also implanted with a phosphorus layer in the top, so they have a high phosphorus content in the top of the surface of these devices, which is important later on. So basically if you cool these devices down to a moderate temperature, I think these are 18 Kelvin, you basically see transistor characteristics as a function of the backgate bias and the source drain bias. Quite standard stuff, nothing too sophisticated there. If we look now at the 1D profiles of these devices, I explained earlier that we implanted the devices so there's a high donor concentration in the near surface away from the box or the buried oxide here. So what I've been able to do is just do a very rudimentary 1D model of these devices. If you take a cross-section through the actual silicon layer and look at the electron distribution in this region as a function of backgate bias here. And this is basically what you see. You get a depletion region with a negative bias and obviously positive. You get an accumulation, and then you get this sort of two DEG sort of forming far from the actual phosphorus region, the peak phosphorus region, towards the buried oxide layer here. So with this in mind, you can actually model it quite simply just using a normal transport equation and fit these IV characteristics quite simply. And it all fits quite well in terms of the DC measurement technique. So with this, we've been able to perform the Fourier transform infrared spectroscopy. So how this works, this is a nice slide that I only just put in, but it's quite important. But basically, what we have is a non-coherent light source. Basically, this is just a glow bar that provides the light for the system. You then have a Michelson interferometer, which consists of a fixed mirror and a moving mirror here, which might give you car sickness or something if you work it too long. But basically, what that creates then is an interferogram of light. So changing in intensity is a function of the moving mirror position and the path length. So, so then you shine this on the sample meter, I'll stop the moving mirror. So this is, again, the same scheme, but in a more stationary system. You basically then shine the light on the actual sample itself. So this is the idea of the interferogram that's incident on the active region of the device, which I've shown in blue. And then if you look at the current response in this device, you also see an interferogram, somewhat different to the light intensity, but you get an interferogram itself, and this is the interferogram from the sample response. So if you then Fourier transform that interferogram, lo and behold, you get the sample response as a function of wavelength. So what you see here is a few peaks that correspond to the transitions between the first couple excited states in our system here. So this spectrum is interesting, but it raises a few questions. Firstly, what's important here is how's the actual mechanism working? Why do we actually see an optical response? And then this question is answered using the theory of the photothermal ionization spectroscopy. Basically here, what we're doing is using the light to excite to an excited state, but then we're using phonons in the lattice to do the excitation all the way to get the electron into the continuum, and then you're left with an ionized donor, which then changes the resistance of the device. This system isn't that efficient because often what happens is the electron de-excites and returns to the ground state without leaving ionized donors. So you don't really detect a large number of ionized donors, but the fact is this technique's very sensitive, and so you still get a very good signal even though you're detecting a very inefficient mechanism. So the next question is why in this typical spectrum don't we see the higher lying excited states? And this again is answered by a plot Gabriel showed yesterday. Basically, if you have a high concentration of phosphorus present, you start to get an overlap of the higher lying excited states, and so they're no longer sharp, and you get a smoothing over. What you do see here is a lot of fringes. This is just a Fabry-Perot interference between the top and the bottom of the sample, and you shouldn't be confused with actual peaks. So this is part of the explanation, but a second explanation I've already hinted at is that strain within this layer will perturb the excited state spectrum. And obviously, the higher lying excited states is perturbed greater than the lower lying states. But on the flip side, this makes quite a handy mechanism to observe the strain in the active region, in the important region within our device. So to explore this further, what we've actually done is strained the layers of silicon, and you can actually see quite nicely a splitting of some of the energy levels. So here with a relatively moderate strain, you can see a splitting by about 20 wave numbers. So just by fitting this to a basic curve, you can see that this is about 40 megapascals in terms of strain. So it's a moderate strain, but there's no reason why you can't use this technique to, in fact, observe a much larger strain. And this was explored by someone else much longer ago. But the fact is that once you get past a certain amount of strain, then you no longer perturb these excited states. So really there's a limit to the maximum strain you can detect with this mechanism. And that's about, I think, from what I understand, the phosphorus in silicon is about 500 megapascals. But from what I understand, this should provide a significant perturbation of the mobility in terms of inside your device. So really, this could be a quite sensitive way of detecting strain precisely in the region of interest of your device, and doing it without destroying your device, with an active device. Okay, so with moving on from that, we've been able to explore a few of the other parameters of this device. I've already alluded to the idea that temperature is an important factor in these types of measurements. So here what we've done is just looked at the temperature effect. And as you can see, in terms of this 2p state, you're getting a peak temperature arising. So the reason why this happens is at low temperature, you're not really exciting many electrons all the way to the conduction band. They're preferentially becoming de-excited back to the ground state. So as you start to heat up the device, then the process of ionizing your donor becomes more and more efficient. However, this has a tail-off again at higher temperatures because you're getting a faster recombination rate of your electrons, and this is because you're getting thermal ionization all the way from the ground state into the conduction band, and this dominates. And so really the FTIR spectrum starts tailing off in that region. So just to say that again, we've actually been able to quite accurately model that by looking at the number of electrons with time in the conduction band. Basically, by looking at the probability of excitation to the conduction band, and then by multiplying that by the ratio of ionization, or the rate of ionization, divided by the rate of recombination you see here. Then you can obviously transfer that to the increase in conductance as a result of the optical excitation, and just using a very rudimentary transport equation here. So then we can fit that with the energy levels and so on. So there's another important factor here that we have the back gate in this device. So the optical response here changes significantly with as a function of the backgate bias. So initially one might think that this would just follow the actual DC current through the device. But somewhat surprisingly, we've found that that's not the case. You get this saturation here, which doesn't follow the current. So in this scenario, the current just keeps going straight up. But the optical response tails off, levels off in this region. So to understand this, we've had to model this quite extensively. So here in the model, what I do is I've replotted a lower current version of what I've shown in the previous slide. The reason for using a lower current is because then you get you don't get any heating in the device at low temperature due to the current flowing through the device. But there's high signal to noise, but it's still the same process. So basically what we've done is looked at the excess electron distribution as a function of selectively optically ionizing a small fraction of the donors within the device. And then if you do that and look at it as a function of the backgate bias, you can see that, in fact, the electrons are deeply affected by the number of the higher density of phosphorus donors towards the surface, away from the backgate. So just by simply integrating this curve and looking and then using the simple transport equation here, very simple stuff, you can actually fit moderately well the actual optical response or the intensity detected as a function of backgate bias. So it's still not perfect, but I think basically by understanding sort of the trapped charge in the region, you could probably make that a lot better. This is all very preliminary modeling that's occurred here. So, okay, so that's basically just understanding the device in a very simple way. We then took this device and wanted to look at its response with time to see how fast it could respond. And I think ideally we'd like to do a lot of free electron laser measurements with this device. We haven't done a lot yet, but basically what I've got on this slide is where we're at so far. Here basically, as you change the free electron laser wavelength, you get the optical response. So this is exactly the same as what you see with the photoluminescence. The FTIR spectrum. But here what's interesting, if you stick on frequency, on resonance at this point, this is what you see here, you start to see a modulation occurring. Now what this is a result of is the free electron laser, this incident on the sample arrives in very short micropulses at a repetition rate of about 60 megahertz. So basically what you're seeing here is the sample being modulated at 60 megahertz. So I guess what we see here is that actually we've got quite a fast terahertz detector in the sample itself. So also I've been exploring this further more recently and set up a more RF related system to actually, I'm not sure how clear it is. Anyway, the device is in here and we've got RF lines coming down to the sample. So then by looking, just simply modulating the source drain bias, you can look at the optical response at very fast speeds. So here we're actually limited by hardware, but we're able to get a very reasonable optical response using 80 megahertz modulation on the source drain contact. So already quite exciting that we can detect terahertz at that kind of speed with just a very simple transistor device. So I don't know how much time we've got to go into this, but also we've started shrinking these devices down to much smaller sizes. So here's the optical response of a 150 by 150 micron device, still quite small. The FTIR spectrum is not that nice, but what we've actually found is by modulating the gate bias, you can in fact clean up the spectrum quite nicely. I'll explain that more in a moment. We've actually, you can compare that to the basic absorption in a bulk sample, and you get a very similar spectrum. So basically what we're seeing is much higher lying states in these samples. But we've also moved down to, again, smaller devices again. These are 40 micron by 40 microns, so still very historic technology, but we are getting to a much smaller device size. So what's interesting with this is after you do the modeling and work out how much current is going through the device as a result of the optical excitation, you realize that the time average number of donors that we're exciting is only around 100. So really we're quite sensitive to just a small number of ionized donors, even in this relatively large device. So again, by comparing this to between all the different device sizes, you can see you get a relatively similar result when you just do a regular FTIR spectrum. There's a bit of perturbation because of the stress and strain in the actual device layer in some of the smaller devices. And I think also there's a bit of problems with the oxide quality, being a very poor quality oxide. But what's interesting is with all these samples, if you do a gate modulation detection method, you can actually clean up the signal quite nicely and see a lot of the much higher lying states. So just quickly, why this is happening is that really by modulating your gate, you're changing the electrostatics in the region just near the backgate region and that region. And as a result, that's the region you're sensitive to in your actual detection mechanism, and so you're actually looking at the donor concentration in that specific region. Okay, so that's the end, really. Basically here I've been able to show that we can do very sensitive strain measurements within our field effect transistors in a very specific region that is important to the device. I've been able to model the optical response of these devices and also show that these devices can actually respond quite fast to terahertz radiation. Okay, thank you.
The paper is open to questions.
Yeah, you probably guess my question. So in talking about the strain and the measurement, in talking about the strain that you have here, how was so you impose strain on these systems? How was that done?
Yeah, I didn't actually describe that because it's not very beautiful. It was basically what happened is I had this bottom sample, I had it poorly mounted. And so basically I just bent the sample mount and popped the sample off and then thought, okay, it's ready to go, and stuck it back down and happened to be a whole bunch of strain in there. But with this in mind, there's actually, it's quite easy now to set up a system where this strain is adjusted. So you can actually live modify the strain of the device. These device sizes are 8 millimeters square, so it's not a small wafer that it's mounted on. And what's interesting though is because I think it's the silicon on insulator, I think the strain is quite easily transferred to just that top region. And I think that's actually quite important. And basically this strain is locked in. The device is ruined or strained permanently.
So you're saying by bending, basically, you induce the strain.
Yeah.
And so that would give you a variety of options. That's basically one method in which they do through piezoresistance detect strain. So that could be an independent measurement as well. However, here you're really looking at one very specific region with respect to depth of that feature.
Well, I mean, what's interesting here is that if it's not homogeneous strain throughout this device, you wouldn't get sharp lines. Mm-hmm. So that's quite... in a way, that was a bit surprising to me. Really the depth of this layer is quite large at 1.6 microns. I mean, sure, I think the future is really narrowing these devices down, making them very small, and then then the strain is homogeneous because by definition the device size is small.
Yeah.
But
the worry is that because you're doing these at cryogenic conditions, and you have dissimilar materials there, as these devices get smaller, the coefficient of thermal mismatch will probably induce overlapping strain fields that you will be able to measure, hopefully.
Yeah, I mean that's it. Is that, I guess in a lot of ways, people wouldn't be aware if they've got some kind of strain
Right.
that separates this. That's right. So in a way, yeah, I mean, for the moment, it's great. We see, in some devices, we can see a very, moderately sharp line, which is, positive. But, yeah, who knows? When we start going to very smaller devices, and then, if you hit it with a different type of laser, then you can strain it or do a lot of stuff. So, yeah, in a way, it's quite powerful.
The point is that even with the point is it's electrically protected. It's as small as your transistor. So if you can address a transistor on a die, and there's a phosphorus atom nearby, you will see this.
Yeah, if the strain field exists.
Does this transistor have strain? Because that's the wonderful thing about the electrical protection, and it doesn't seem that we've got loads of sensitivity left, but at the end now we're seeing just 100 impurities.
Yeah.
Even with these large devices, which is not a whole lot. Right. Okay. And what it means is if there's any, essentially, if you have some phosphorus anywhere near a channel,
Yeah.
you can say you can go to that channel, do the electrical measurement, and dive into strain.
Yeah. I mean, another important point is that, often a lot of these layers are transparent to terahertz radiation. I mean, polysilicon, is moderately transparent. As soon as you've got a gate, a metallic layer, no, it's not transparent. But in a way, it's quite easy, relatively easy to couple light in through the sides or something like that. So, I think it's quite.
In your conclusions, like you say, you can detect the signal from about 100 revert atoms. I guess you're not detecting spin echoes. What are you detecting from them? I didn't catch that part.
So that number basically is just the time average number of ionized donors that are a result of that excitation process. So basically, what in these measurements, we've got quite a large background current going through the device. So then we slightly perturb that background current by just exciting a few donors. So the number of donors that we're exciting through this optical process, it works out to be around 100 atoms. So in a way, I guess what I'm saying is that we're already sensitive to a very small number of donors, even though we've got this huge device with current flowing everywhere. But really, we just have to narrow down the device size, and then we've got something much more powerful.
You can therefore lock it.
Yeah.
Locking
And optical modulation.
Base lock.
It's locked in two ways, often, both
Yeah.
electrically locked in at 80 megahertz. It's doubly modulated than there's the opposite frequency experiment, so you can see very few numbers, even on these huge ancient devices.
Yeah.
Okay. Thank you. Are there more questions for this talk? If not, let's thank Dr. Villis again. And there's a poster session and coffee break ongoing now. I suppose the poster session must be in the hallway.